There's another cool method to identify local maxima or local minima, which is the second derivative test. So to introduce the second derivative test, I will first recall just quickly the first derivative test as well. So this was the first derivative test. We remember we look at the first derivative, which is the slope of the tangent line, and then we look if it changes from positive to negative or from negative to positive. Right? So if it changes from pos to neg, then we have a local maximum, and if it changes from negative to positive, then we have a local minimum. If f prime does not change the sign, then there is no extremum at all. The second derivative now uses what we have learned before, the concavity, concave up, concave down. Let's see how this goes. So here it is. Second derivative test. So we assume that f double prime is continuous at a. And then if f prime at a is equal to 0, so that f double prime at a is positive, okay, then f is a local minimum. Do you remember? F double prime positive means concave up. So we have a smiley face condition, right? So it's a happy face. Clearly, the point where the derivative is 0, which is here, okay, so at this point the derivative is 0. This is clearly a local minimum. In the other case, when f double prime is less than 0, we have the sad face situation. The point where we have a horizontal tangent is a local maximum. Finally, if f double prime is equal to 0, then we can actually not say anything. It can be a maximum or minimum, but it could also be neither of those. So let's do an example. So here I show you again the two criteria. So f double prime positive, local minimum, f double prime negative, local maximum, at points where f prime of a is equal to 0. The example is f of x is sine square of x. And here I plot you the function, and you clearly see that it is a periodic function, and it has maxima and minima, and they oscillate up and down and up and down. Let's try to apply the second derivative test for this function. So what do we need? We need f prime and we need f double prime. So let's compute those first. F prime of x equals 2 sine x times the inner derivative, which is the derivative of sine, and this is cosine. And then we need to find the zeros of f prime, right, which are the critical numbers of this function. So f prime is a product of sine and cosine, which means it is 0 whenever sine is 0 or when cosine is 0. Right? Sine is 0 at 0, pi, 2 pi, 3 pi, 4 pi. Cosine is 0 at pi half, 3 pi over 2, 5 pi over 2, etc. So together we get at all half values of pi, we get a 0. Maybe I write it like this. So 0, pi over 2, pi, 3 pi over 2, 2 pi, etc. But then also we can have negative values, minus pi over 2, minus pi, minus 3 pi over 2, etc. also in the other direction. So there's an infinite number of zeros for f prime. Now to identify them as local maxima or minima, we need f double prime. So let's take the function here and differentiate again, and you see we need the product rule. So f double prime equals 2, and then I differentiate sine, which is cosine. So I get cosine square, and then plus 2. I keep the sine, and I differentiate the cosine, which is minus sine. So then this together is 2 times cosine square of x minus sine square of x. And now we sub in all those critical values. Minus 3 pi over 2 minus pi over 2, 0 pi over 2 pi, 3 pi over 2, 2 pi, etc., etc. So let's start with 0 again, and then let's work our way up and down. So f double prime at 0 is what? So we sub it in here. Cosine of 0 is 1, sine of 0 is 0, so this is 2, which of course is positive, so we have a local minimum. Second derivative positive is concave up, smiley face, so it's a minimum. Let's do the next point. F double prime at pi over 2. Again, we sub it into f double prime. This time cosine square is 0. And sine of pi over 2 is actually equal to 1. So then we have minus 2. which is less than 0, and we have a local maximum, which is right here. And so on. So let's do maybe the next one, f double prime at pi. You can easily find out that this is again equal to 2, positive, local min, and this is a point here. And then if we do f double prime at minus pi over 2, it is minus 2, less than 0, so I have a local max. So of course, from the picture you see that max follows min, follows max, follows min, but then the second derivative test gives us the same result. So here I write down both tests on one slide for you. Just remember that for the second derivative test, you look at the second derivative, like here. Okay, and then if you have the concave up situation, a smiley face, you find a minimum. If you have a sad face, f double prime less than 0, you have a local maximum. And if f double prime is equal 0 at a point, then, well, this method doesn't work. Hey, Tolo, what's up? I love to hear what you have to say about concavity. Show me. Concave down, concave up, concave what?